that I forgot earlier is that there'll be a poster session during the coffee break after Andrei's talk. So there are a number of posters on the TV screens in this main area, and so there'll be space for discussion with the people presenting. In today and tomorrow and Thursday and Friday, there'll be poster presentations on those screens. The posters will be shown for the whole day with discussion during the coffee break in the afternoon. So the first talk now in the afternoon is by Andryi Haydys so on an index theorem for Z2 harmonic spinors. So thank you very much, Andrei.
Thank you. Thanks the organizers for the invitation. So the main player for today's talk will be what is by now known as the Z2 harmonic spinor. So let me explain to you first what is the meaning of that. Well, a prototypical example for that is if you take a complex number z and think of this as a variable. So you take the square root of z, and this is a function on the complex plane. But of course, as you have been explained very well in your basic analysis, complex analysis course, this doesn't make any sense, because if you take a loop, the value changes. So this is really a two-valued function. There are many ways to deal with this. So typically, we are not very happy to deal with two-valued functions. Some people are. But what you can do, you can consider the double branch covering corresponding to this function. So you take w squared equals c, and think of your square root function as an odd function on this Riemann surface. Or equivalently, you can, so if you know this by x, you can take x, so the associated line bundle, so the real line bundle, let me denote this by Kelly I, and this is a line bundle over C star, so the unique non-trivial line bundle, and square root of z can be thought of as a holomorphic section of this line bundle complexified. Of course, it is defined only on the complement of the origin here. And this approach will be somewhat better suited for us. So here is the definition. A two-valued function on, well, let me immediately say a two-valued harmonic function on a Riemannian, of course, oriented manifold M is a triple U, sigma, and I, such that the following holds. So first of all, I is a real Euclidean line bundle over the complement of sigma. So it's not defined everywhere on M, as it was not defined everywhere on C. So this is real Euclidean line bundle, and as such, it has a unique canonical connection. So U is just a section of this line bundle, but let me stress is defined on the complement of sigma, and the Laplacian of U is 0, again, where it is defined. And also, we require that U of M approaches to 0 as M approaches sigma. Right? And if you have such a triple, hopefully I didn't forget any important condition.
Do you want sigma to be codimension 2? Do you want sigma to be codimension 2?
That's a good question. So at this point, the only thing I want to say here is that sigma is closed. But of course, the interesting case is when sigma is of codimension 2, which allows this line bundle to be non-trivial. Right? Otherwise, if you have just an isolated point, if you have a stratum of higher codimension, it's a removable singularity by classical theory. All right.
So right now, you say it's two-valued. There's an involution, perhaps, where it changes sign? Is there a plus-minus sign rule?
So think again of square root of z, right? So you may think of this as a two-valued function which has two values at each point, or it's a single-valued section of a bundle. Right? For me, it will be a single-valued section of a bundle which has a twist as you go once around sigma. And that's where the multi-valuedness is hidden. Again, for whatever reason, the terminology became Z2 rather than two-valued, and I will call such an object a Z2 harmonic function. And in the same fashion, you can define Z2 harmonic forms. Again, they are triples, omega, sigma, I, such that d plus d star of omega is 0, and the rest of the conditions. So the equation is on the complement of sigma, and on sigma we require that omega vanishes, or rather the absolute value of omega. Or you can define in the same manner the two harmonic spinors. Right? Again, here the equation is deep C equals 0, where C is a section on the complement of sigma of S tensor I, where S is a spinor bundle of N. All right. Well, so an important remark here is that you should think of sigma as a variable in this problem. So as I said, a Z2 harmonic function is not just a function, it's a triple. So for this talk, the line bundle will be sort of determined by sigma by asking to have a non-trivial monodromy along each small circle, which in circles a codimension 2 stratum. So I will often drop I from my consideration, but sigma is part of the problem. And this makes the problem highly nonlinear. All right, so in this talk, I want to focus on what can be said. So the main question will be what can be said, in fact, about sigma.
So there's no rule that you can extend across by 0, or
well,
approach sigma?
No, actually, you can't extend by 0 because your bundle doesn't extend. So it's a non-removable singularity. And yes, it's a very good remark. So that's a source of main interest and main difficulties in this setting. So this non-triviality of I is really important. But before coming to that, let me explain you why would you even consider anything like this. So there is a growing literature on such objects, and the main motivation, first of all, there is a classical motivation. So this is a classical theory of minimal surfaces. So if you have a minimal surface in an Euclidean space, this is locally described by a nonlinear equation. But if you linearize this equation, you have a harmonic function. But now assume that your minimal surface becomes a double branched cover. Right? In that setting, what you have, you don't have just a harmonic function, but you have a two-valued harmonic function, or in other setting, a Z2 harmonic function. Now, the motivation for me personally comes from gauge theory. And in here, such objects appear as, these are models for ends of moduli spaces. Maybe to give some more concrete examples, so the moduli spaces which I keep in mind are the Seiberg-Witten equations with n spinors. Or Waffer-Witten, Kapustin-Witten, and there is a whole series of gauge theoretic problems where such objects do appear in the compactness setting. And it also appears in the higher dimensional gauge theory, so for G2 instantons and spin 7 instantons.
That's the holonomy of the base, not the fiber group.
That's exactly correct. So the setting is this. So you have a big 7-dimensional manifold, M7. In here, you have a 3-dimensional submanifold, in general singular, which is associative. And on this, you have a section basically of the normal bundle which has two values. This is an object which appears in the blow-up sequences of G2 instantons. So indeed, there shouldn't be mixed. Also, this appears in G2 geometry. So more precisely, in the following setting. So assume you have a G2 manifold which fibers by 4-dimensional fibers, and these 4-dimensional fibers are assumed to be co-associative. Then you can show that if they are compact, they must be K3 surfaces. And so a generic K3 surface will be smooth, but there will be some singular ones. And so you have a 7-dimensional manifold again, or a 3-dimensional base. And in here you have a link which describes where the singularities of the fibers appear. And in certain limit, so that's Donaldson idea, the G2 structure corresponds to a map U from B3 minus L into R319, which is positive and maximal. And as you go along a circle, so along the meridian, you have a non-trivial monodromy here. So that again appears in here, and also appears in calibrated geometry. Namely, so if you have a Lagrangian submanifold, then the infinitesimal deformation of a Lagrangian, say of a compact Lagrangian submanifold, is given by a closed form. But now, if your ambient manifold is Calabi-Yau and your submanifold is special Lagrangian, and you ask for the deformations to be special Lagrangians, what you have is a harmonic one form. But now, imagine again, so you have a family of special Lagrangians which become, in the limit, a double branch covering. And so the infinitesimal deformation of this situation is again a two-valued harmonic one form. So again, the object which fits very well into this framework. And all this puts some evidence that there is great interest in such objects, even though they are not, there is still a lot to study. In any case, so if there are no questions to that,
Where does the 19 come from?
say it again.
Where does 19 come from?
Second
19, yes. Indeed.
So I think in this picture, if you take the derivative of this map U, then you get a three-plane in R319, which you think of as the second cohomology of K3 surface, and this is picking out the self-dual.
Absolutely, yes, absolutely. Okay, so let me give you a couple of examples. So we had already one example. This is the square root of z. The second example arises as follows. So we take M to be the flat C2, and I will take H to be any holomorphic function. And so what I can do, I can take sigma to be the zero locus of H, and I can declare U to be the real part of H to the power 1/2. Again, in the same sense, so square root of H doesn't exist as an ordinary function, but there's a two-valued function or as a section of a proper line bundle, it does exist. And of course, since it's a real part of a holomorphic function, this is a Z2 harmonic function. Now, why is this example? So it's very simple, but it's also very interesting for the following reason. Maybe before coming to that, let me do the following. So I could declare omega to be the differential of the real part of H to the power 1/2. And this is almost a harmonic, Z2 harmonic form, except if I have simple zeros of H. I take the differential, so the differential, the norm of the differential doesn't need to go to 0 as I approach sigma. But actually, this is not a big problem, so if I take here 3/2 instead of 1/2, I still have this property.
So in your definition somewhere, does it say that this function, this harmonic function is supposed to be bounded? Or
Yes.
These are unbounded objects.
Yeah, so well, you know, for most of the talk, I will assume that M is compact. In that, and since U goes to 0 as you approach sigma, the singular set, it must be bounded. You know, to write down the examples, non-compact manifolds are better, so in that sense, they are unbounded. But, okay. Now, why is this interesting? If I take H of ZW to be ZW minus T, where T is a complex parameter, so what happens is that sigma T is smooth for T non-zero and is singular for T equals 0. Right, and what we see is that here, in this definition, the set sigma may be singular itself, right? And if you have a singularity, at least in this example, this appears in complex codimension 1. So it's a non-generic behavior, and it's easy to understand that this is a general feature.
Sorry, suddenly sigma has a parameter T. What is that?
You know, it's just a parameter, so I can take. All right. And so, you know, the next example is less explicit. So Taubes and Wu constructed Z2 harmonic 1 forms on R3. Well, the singular set looks like a collection of 4 rays. They actually have several examples, but these examples are much less explicit than the previous ones. But in any case, so examples do exist. So we must ask ourselves how singular can sigma be? And the most general answer to these questions that we have is the following theorem. Which is due to Boyou-Jean. Theorem is let omega sigma I be a harmonic, well, Z2, harmonic one form, or a spinor, it doesn't matter for that setting, on Mn. Then sigma is n minus 2 rectifiable, well, at least provided that n is at most 4. I'm not sure that that this bound is really essential, but this is what Boyou has in his theorem. But in any case, so we know, maybe to explain, n minus 2 rectifiable just means that away from some singular set, this is n minus 2 submanifold. And this the singular set here has 0 is a vanishing measure. But saying that the singular set is a vanishing measure is not saying much for geometric applications. And so we would like to know slightly more. Can we say that singularities are isolated or anything of this sort? Now, so maybe one more thing that I should remark is that the first dimension where these effects occur is 2, but in dimension 2, it turns out that you can express the two harmonic one forms as square roots of quadratic differentials. And so we know about this object as much as, some people wouldn't agree. So some people say we still don't know enough about these objects, but for Riemannian geometer, we know already quite a bit. In any case, so the first dimension where the things become interesting is 3, and that is what I will concentrate on from now on. So M3 from now on is a closed, oriented, and Riemannian manifold. And C will be a section of the spinor bundle, except that I may allow here a twist by a unitary rank 2 bundle, and I will have this twist by a line bundle. So this is an SU2 bundle. Now, since we are in dimension 3, any SU2 bundle is topologically trivial, so it's basically only the connection here which enters into the story, which is important. And I will pick a connection A on this bundle. And in this setting, if we choose a Riemannian metric G and a connection A, we can ask for Psi to be harmonic. And again, this is on the complement of sigma. That's the Dirac operator indeed. So the standard twisted Dirac operator, so there is nothing happening here. And let me denote by R the space of pairs GA, where G is a Riemannian metric on M, and A is a connection, a Hermitian connection on E. In here, we have the set W. So this is a set of all those pairs GA for which there exists a non-trivial Z2 harmonic spinor. Now, the conjecture is that if you remove this set where we have a non-trivial Z2 harmonic spinor, then this is, well, open. Maybe the better way to say is this. So the codimension of W in R is 1.
So I guess for you, E is a trivial bundle, so you could just say it's matrix value in one form?
Yes, absolutely. You know, it does appear here, anyway, yes, it doesn't matter. Right, and so, moreover, W admits a stratification that is W can be written as W0 union with W1 union WK and so on, W infinity. And what is what here? Well, W0 is a set of pairs GA for which sigma is smooth. By which I mean, so if we are in W0, we know there exists a Z2 harmonic spinor Psi, but Psi is a triple, and so the singular set here, the branching locus, is asked to be smooth. So I don't write, you know, all entries very explicitly, but hopefully it's clear. W1, again, is a set of pairs where sigma has a unique self-intersection. And so on. So WK is a stratum where you see K self-intersections if you count with multiplicity, and W infinity is the rest. And the conjecture is that the codimension of WK in R is K. Yes, it's a good numerology. K plus 1, indeed. Thank you. So by the way, all what I'm saying today is a joint project with Raif Matseo and Ryosuke Takahashi. All right, and so in some sense, the rest of this talk is to provide some evidence for this conjecture. But the big picture is like this. So you have a big parameter space. So this is schematically R. In R, you have some walls. Maybe like this. So here you have W0 where the singular set is smooth. But sometimes you have points where the singular set is itself singular. But these come as a higher codimension stratum. So why is this important? This is important for many reasons. So if this conjecture is true indeed, then in the gauge theoretic problems, for example, that I mentioned, this means, for example, if you choose your parameters within the chamber, your moduli space is compact. So you may hope to define an invariant. But if you change, if you go from one stratum to the other one, your invariant may change, but it will change by a wall crossing phenomena. And since here on this generic part of the wall, you have a singular set, you have a smooth singular set, you may still hope to work out the wall crossing phenomena here. At least technically it's conceivable.
Could you go in, make more precise the self-intersection of sigma? So is sigma an inverse submanifold?
Yes.
So you're assuming, so that it's not worse than that, just an inverse submanifold can cross itself.
I'm slightly vague here. So you can imagine that you have, a transverse self-intersection, but then you can, of course, obtain a non-transverse self-intersections. I'm ignoring this here.
I'm looking at this example that you drew on the board before, where it's definitely not a manifold, and you have some kind of, maybe it's like model of a cell complex or something like that, not on a manifold. But you're in the situation you're describing, your conjectural picture is that.
Maybe I should have said better, sigma is an embedded graph with k vertices. Does make sense? So in here, we don't have like transverse self-intersections, but it's almost like having two lines intersecting at a point. You have here 4 edges, but that's good enough.
You're thinking that topologically it will, in particular, always have the multiplicity of a vertex is always even?
Yes, it must be even for topological reasons, because otherwise we can't define a bundle which would have non-trivial monodromy. We don't know what are the worst singularities. We don't know whether they are isolated, may be worse. But what we observe in examples and in the general theory is that whenever you have, so each singularity brings in negative index. So they should be more and more common. They should be less and less common.
Right, so suppose you have suppose it is a graph with only finite many edges. What is the number that when you say it has? I guess I can't really see when you go down. W2, for example.
Yes.
For W1, you'd have only one place where it's topologically like this.
Yeah. So
can you have more edges emanating from the vertex?
yes.
And how do you count that?
Let me explain this to you. So a thing which is in W1 is something like this. Right? In W2, what you can have is either this one, or you can imagine having something like this locally, and so on. There are degenerate cases where, so I will assume for this talk that they have all different tangents at the vertex, at a given vertex. But let us ignore, the fact that they may be tangential.
So in this picture, right, you do not, you have one, you'd like to think of this as a crossing of one manifolds, but one is not smooth, right? It has two different.
Oh, no, I see.
No, I know in those pictures you've drawn, but this other one.
In here?
Yeah. So that picture is a bit different in that it's not a smooth crossing of two smooth.
No, I do not insist that the crossing is smooth. So something like, well, let me try to be less regular. Is fine. Yeah. So this is the same crossing as this one.
Yes.
Topologically.
But the smooth structures, I mean, is.
Yeah.
Good.
All right.
So can you say, I think you said it's compact within the rectangle?
I can't hear, excuse me.
You said it's compact within the rectangle? Or what sense? Are you assuming like the energy is bounded?
So that picture in the rectangle is not happening in the manifold. That's in the parameter space.
Yeah, so there's a picture for R, right, for the parameter space.
It's
So
an infinite dimensional thing, but you've got some finite codimension subsets.
That's exactly correct. So you have a certain compactness statement which says that if you have a sequence which diverges to infinity, then you can produce out of that a Z2 harmonic spinor. And in particular, if a non-trivial Z2 harmonic spinor. And if there are no Z2 harmonic spinors, you can't have sequences which go to infinity. In the moduli space which I'm studying, so for example, the Zyberg-Witten moduli space with n spinors. Okay. Now, fix a Z2 harmonic spinor, let's say psi sigma, and let me drop I because I will not play any role in what follows. Such that sigma 0 is smooth. Now, what is going next, I will try to describe what we know already and what justifies this conjecture. Where sigma 0 is, which is sigma, and let us denote by L, so this is L of sigma psi, the linearized operator. So I don't give you any expression for L because it's not really very helpful. You can imagine there is a way to linearize the problem. And the theorem, due to originally Takahashi and later due to Berger, proved slightly more and by different methods, is that if sigma is smooth, and how do I want to put this? And psi is non-degenerate, then the index of the linearization is 0. So I will explain in a minute what is the meaning of psi being non-degenerate, but let us not worry for now. But what you should maybe be surprised a little bit about the statement is that the index is 0. So we have a nonlinear map of index 0, and then we expect that whenever we have a solution, we always have a solution nearby. This doesn't happen here because of the following reason. So if psi is Z2 harmonics, and any t psi is Z2 harmonic for any t in R. So if you have one solution, we have the whole one-parameter family of solutions. But this means that the linearized operator has a non-trivial kernel. And since it has index, it means that the core kernel of L is non-trivial.
So could you clarify? So here the domain of the linearization is considered to be the complement of sigma, but maybe with a Dirichlet. I mean, to get a Fredholm problem out of it, what is the operator is defined on what space?
It's a slightly involved question. I will answer this slightly later, but let me not go into details right now. Indeed, I mean, it's a non-trivial problem how to linearize this problem. But as I said, I will give a partial answer to this slightly later. So what we have is that the core kernel of L is non-trivial, and generically, the dimension of the core kernel of L will be 1. And this is the reason that we have a codimension 1 walls, at least if sigma is smooth and psi is non-degenerate. Right, so we don't expect to have the two harmonic spinors for generic parameter. But now let me explain to you what is the meaning of psi being non-degenerate. Now, let us assume for a while that our ambient manifold is flat R3, which we think of as R times C. And in here, sigma is simply the straight line, which I will identify with R cross 0. And in that case, you can write psi as some coefficient. Let me know this by A. So the variable here is t, and the complex variable z. So this admits an expansion of the form a of t z to the power 1/2, b of t z bar to the power 1/2, plus higher order terms that we don't care about. In any case, so if you have a Z2 harmonic spinor, we obtain the boundary value of psi, which we declare to be the pair A and B, and these are just this is a pair of complex valued functions on sigma. And now I will say that psi is non-degenerate if this pair doesn't vanish anywhere. So if A, B is non-zero for any t in sigma. You may wonder if this is really a true condition, or maybe this follows already from what we have. There are examples which show that this is not any Z2 harmonic spinor is non-degenerate. So
you're saying it's not 0, 0. It's not 0 in R2.
It's not 0 in C2 for any t. So I will explain a little bit why this is a reasonable condition. But let me explain now how to obtain a deformation operator. It doesn't matter. So to define what is non-degenerate, so I could have taken M to be non-compact and sigma to be smooth. So it works just the same. It's a local statement. For whatever sigma one-dimensional line in a three-dimensional manifold, and if you have a Z2 harmonic spinor, which is only defined in the neighborhood of sigma, you can define its trace. That's not a problem. The problem is more to prove that your deformation operator will be Fredholm. And for that, you need compact setting. You need a compact manifold. If it's non-compact, then...
You wanted to explain later what the operator M is, right?
I want to explain this right now. OK. So what I will do now will be vague and, strictly speaking, also wrong. But nevertheless, let me do. So let us take a family of Z2 harmonic spinors, psi s and sigma s, where s, it's just a real parameter. I don't know, such that this is just a family of Z2 harmonic spinors. Again, let me assume for simplicity that my base manifold is again R3 and sigma 0 is R times 0 as before. So what I have is this. I know that if I apply the Dirac operator to A, well, in fact, let me assume also that sigma s is a graph of some function zeta s from sigma to c. And so what I know is that my spinor is of the form z minus zeta s of t to the power 1/2 b. So A depends on t, but let me skip this. Z minus zeta s of t to the power 1/2, and I have to take 1/2 plus and so on. And I know that this is 0. So have something like this. But now let us differentiate this very naively. Let us take d by ds when s equals to 0. And so what we have is d applied to. So if I differentiate this with respect to s, I will obtain a spinor which is of the form a z to the power minus 1/2 and b, a zeta of t z to the power minus 1/2 and b zeta bar z bar to the power minus 1/2 plus and so on equals 0. Right, so what stands here as an argument is some element phi, which is also a section of the spinor bundle twisted by I. But the difference to the previous setting is that as we approach sigma, it blows up rather than tends to 0. Right, so now what we can say is that our linearized operator L is a map from, well, if you look carefully, this is still in L2, right? So we can define this as a map from L2 m minus sigma into whatever the space is. So in here, this is r to the power minus 1 L2 m minus sigma. Yes. So I'm focusing here on the behavior near sigma, right? In that sense, we obtain here a negative power to minus 1, but locally this is from W12 into L2. And so let me denote by Z0 of sigma to be the space of those phis in L2 m minus sigma such that d of phi is 0. And the first proposition is that the dimension of Z0 of sigma is always infinite, whatever sigma is. So in other words, if you recall, in my original definition of a Z2 harmonic spinor, I required that the norm goes to 0 as we approach the singular set. What I'm saying here is if we drop this condition, we immediately obtain an infinite dimensional thing, an infinite dimensional space. That is, to have a spinors which goes to 0 near the branching set is an exceptional situation, unlike if you drop this condition. So this condition is really important here. Now, the second proposition is that similarly as we had the expansion for the two harmonic spinors of this form, for any L2 Z2 harmonic spinor, we also have an expansion, but this starts with z to the power minus 1/2, and some function d z bar to the power minus 1/2 plus, and so on. So again, we have sort of a boundary value, which I will still denote by b. This is now a pair CD. Again, this is a pair of, let's say, smooth functions on sigma with values in C2. But now let's stare at this formula that we had already before. And if you look at the boundary values of the deformation, the geometric deformation, the spinor arising from the geometric deformation, this is not a pair of arbitrary functions. They have a very special form. And so this means that if L of phi is 0, well, how should I write? If phi arises from the deformation of the two harmonic spinors, then how CD must be a zeta b zeta bar for some function zeta, and this means that if I take a d bar minus b bar c, I will have 0. Right, so let me denote this expression by T A B of CD. Now, so what did we obtain? If we fix the two harmonic spinor psi, it gives us a pair of functions AB, which we interpret as a trace. And if we have a deformation of this, if we have a one-parameter family of the two harmonic spinors, which ends at this the two harmonic spinor psi, then it must have an expansion of this form, where the leading coefficients satisfy this equality. And now the proposition is, so this is 3, the boundary value problem TB phi equals 0 is elliptic and self-adjoint. So, and since it's self-adjoint, it means that the index is 0. Right, but in here, in all these considerations, I assume that my sigma was smooth.
Sorry, so there are two operators, B and T is what?
I should have written, sorry about that, T of B of C. So this is this expression in here. So my initial point gives me a pair of functions, and this gives me a boundary condition, and this is how I abbreviate this. Now, it turns out that, as I said, this computation in here is not quite justified. So if you do a clean computation of the linearized operator, it turns out that the kernel of, well, let's say, of this problem, do I have a star? Doesn't matter. Contains the kernel of the linearized operator. So that's as far as we can prove. It seems that we could have picked up some non-geometric elements in the kernel, but at least all geometric deformation vectors are in the kernel of this boundary value problem.
So could you now say, phi is actually, if you just want to count the dimension of the kernel and the co-kernel, phi is required to be smooth on the complement of sigma and to go to...
Right. So here, phi is required to be in L2 m minus sigma, and I don't know, let's say smooth on m minus sigma. But we don't ask phi to go to 0 as we approach sigma.
So, I mean, you could actually just say L2 intersect C1.
Whatever you wish, yes.
So, and then it's, for the co-kernel, this is landing, co-kernel in one space. So it's from that space to itself. When you look at the adjoint, so
I'm slightly vague here, so to do this properly, you should pick here a weight and consider phi in certain weighted, well,
it's a weighted L2 one space.
yes, in L2 intersected with, say, W12, and the image will be in, so this is in rho to the power mu minus 1 L2. Sorry about that.
What was the length in Z?
Yes, that's the distance to sigma. Okay, but I think I already running out of time. So this was all valid for the case when sigma was smooth. But actually, as I said, if you have a singularity, so if you have a picture like this, it turns out that for each such singularity, we still can define an elliptic boundary value problem. The difference is that here you have to consider, you have to blow up this point. So geometrically, you consider here the sphere, and you remember the tangent vectors of the edges. Again, the picture is schematic, so I'm fine when one of the edges goes like this. So what this means then is that we have a sphere, and we have a number of points on this sphere. And at each of those points, we have the limiting boundary condition. And if you compute the corresponding linearized operator and you take its index, it is 0 as if sigma was smooth. So there is a 0th amount minus some non-negative number. So the sum over all vertices. and this is less or equal than 0. Which means that, what I said already, that each singularity of sigma brings in some negative contribution to the index. So the overall index becomes more and more negative. So I think I don't have any time left, so let me stop here.